topic, which is momentum. So let's do a quick recap of where we've been. We can talk about where we're going. So exam 1, kinematics, how things move. Exam 2, dynamics, why things move. In this case, we discussed forces. Exam 3, which is what we're working on right now, is going to talk about energetics and conservation laws. Basically, we're going to combine 1 and 2 together with a new framework. And of course, we're going to have to combine how things move and why things move together, but we're going to take it into consider the energies of these systems. So we've been talking about energy conservation with kinetic energy, potential energy, and work. And today and tomorrow, we're going to be talking about some different concepts with momentum conservation. Today, we're going to talk about linear momentum and angular momentum. So what is momentum? Colloquially, it's kind of this idea of a propensity to keep going, and that's kind of the same. There's actually a mathematical definition that we're going to introduce today. This idea of propensity to keep going reminds me of Newton's first law, which is that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So this idea that you need to apply an outside force in order to change this idea of keeping going, you have this uniform motion. And indeed, we're going to link momentum to force in the next lecture. Today, we're mostly just going to define momentum and use it and be able to try to use it mathematically. So let's define linear momentum. So the linear momentum of an object is just the product of its mass and its velocity. So we have this object here. We can write the momentum is equal to P times V. I want to point out this is the velocity, not the speed. For energy, we've been using the speed. Velocity has a direction, so again, we can think about this mass moving with some constant velocity, and it has a momentum. So momentum is a vector. We're putting the little arrow over top of it because velocity is a vector. And so in this case, the momentum has a direction and it has a velocity because velocity is a vector. So let's just remind ourselves a little bit about vectors. Vectors have magnitude and direction, and they can be broken into XY components. So I know this is one of your very favorite things, is to be able to do things in both the X direction and the Y direction. We're going to go back to that concept again when we talk about momentum. So we can, this equation for momentum, P is equal to mv, it's true for a single particle, and it can be true for a collection of particles. If you have more than one particle, then the total momentum is just the sum of the momentum of the individual particles. And of course, we have to remember they're all vectors, so when they add up, we have to use our vector addition. So that being explicitly stated is that the momentum for a whole system, which we still call P, is the momentum of the first particle plus the momentum of the second particle plus the momentum of the third particle. And we can write this in a shorter form by using this summation over particle I, where we sum the momentum in all the particles. And we can look at the units of this momentum. So the SI unit is a kilogram meter per second, and it's not a very fancy unit or a nice unit necessarily. It doesn't have a new name, but this is the correct units, and you should use that concept obviously when solving problems to make sure that you're doing it properly. So let's think about a collection of particles. If we have a collection of particles like these 4 big particles here, then the center of mass of the system is right here in the middle of these 4 particles. And we've already talked about center of mass and how to calculate it. We don't have to do anything fancy in order to calculate the momentum of this center of mass. We can just add up all the momentums of the individual particles. So we don't have to think about, the mass of each one individually. That's already taken into account with this momentum definition. So let's do an example where we have all 4 particles moving in the same direction. We can see that the center of mass moves along with it, and so it has a total momentum that's equal. And we can actually think about this from the vector addition point of view. If we sum up all these vectors head to tail as we normally would, then this is the momentum of the entire system, which is just the sum of the momentum for all the individual particles. So it has a large momentum. This large momentum, they all have the same velocity in this case, so it just is larger because the mass is larger. This is our second example here. So now we have the same 4 particles, and instead of all moving in the same direction, we're going to have them kind of explode out in all different directions, and in particular in exactly the opposite direction of one another, at right angles and anti-parallel to each other. And so when we do that, this is what the system looks like. And you can see that in this illustration, the center of mass actually doesn't change. And that makes sense again because we're using our vector addition in order to do this. And so the center of mass has zero momentum in this case. We do the same thing where we add up the vectors in vectorial form, and you can see that it comes right back around to the same location. The center of mass does not change. The momentum for the center of mass is zero. So even though all the particles of this system are moving, the center of mass does not move and its momentum is zero. And you will do problems in this class where you have an explosion. When you explode apart something, the center of mass can or may not move. It depends on the exact kind of orientation of the explosion. If you think about one of these kind of like a sparkler canister, where the particles explode out in only one direction, or maybe a fire extinguisher where the particles explode out in one direction, then overall that's more like the last example we saw where they all move in the same direction. If you have an explosion like a bomb that explodes in all directions simultaneously, then the center of mass is actually zero, and you can use this concept to solve problems.